Thank you for the introduction. And as Marco alluded to, we are just getting started sampling the materials search space, right? We have 3.5 million materials and hundreds of millions of properties that are searchable, and we are constantly generating more. So it actually became really a big problem early on that we developed ways to expose this material to our end users all around the world. And in order to do that, we started down the road of developing web applications. The first and most straightforward form was the search page that we put together on our main page. If you will take your browsers and navigate to aflow.org, you will see, let me share my screen here for a moment. Come on, share. Oh, there we go. All right, you'll see that aflow.org has an introduction of various applications, various quantities of materials that we've calculated, and Marco kind of went over that already. We have a quick search, which may or may not be straightforward to see, but if you scroll down to the Mendeleb search button application here, you will find that we have an organizational layout of our materials that is focused primarily on the atomic names and the species involved, right? So you're gonna see, actually, just before I keep going, is this visible to everybody, or rather, does anybody have any problem viewing this? Do I need to... Sorry?
It looks good.
Okay.
It is visible. It is visible.
Good, good. All right. So we decided to start organizing our data sort of as the like just from the periodic table as a straightforward way to approach what we have. And so you'll find that we have lots and lots of other information besides the periodic table. And I'll be getting into that in just a moment. But we focus primarily on our experimental results from the ICSD repository as a way to expose our material and get people familiar with it. We have a lot more than what's in ICSD, but for the purposes of our tutorial, we're going to just stick with the ICSD searches. Otherwise, we'll end up with getting a lot more data that really doesn't help us in terms of getting familiar with it. Once you're exploring the data and you want to get into deeper research considerations, building, say, machine learning models or what have you with our data, then by all means expand your searches to all of AFLOW. And we will continue to grow, which is why we encourage you to keep looking back to our repository for your results. Rather than trying to download it and keep it locally, you'll want to keep coming back and getting our data directly from us because we're curating it, we're adding to it, we're keeping it clean and available to you, right? So, all right, let me get into what this page actually shows you. Okay, so I already mentioned that we have the ICSD search. There is a text search bar that will let you search by names that you see, for instance, here on the periodic table. Sorry, I lost my place a little bit. And so, for instance, if you wanted to search for some material structure that contained manganese, you would click on the manganese button, and you'll see that the text bar is populated with the atomic abbreviation for manganese, right? Now, if you want to add additional materials, which seems entirely reasonable, you would click and is a comma here, right? We're sort of building a list of materials that we want to include. And so we want to go in and add, let's see, what other material we want to add? How about bromine? Where would we find bromine, right? It's BR, and I'm drawing blank. Oh, sorry. It's over here, species number 35, right? And so now we've got 2 species. Now there's a problem in terms of searching our data, right? You can select species, but this will give you a subset of all possible materials that have manganese and bromine in them, right? You'll get binary alloys, tertiary alloys, quaternary alloys, etc. This will explode quite large. So in order to get, say, just manganese and bromine, you limit the number of species that you search for here to 2, right? This will give us 2 species in our search. And if you, for instance, were interested in, say, a range of species, say you only wanted binaries and tertiaries, we also have the ability to set the range, but we're going to skip that just for now. All right, so this is enough for us to get a quick examination of what you can see, right? So you hit search, page scrolls down, and we get some responses, right? Not very many. And these are the default response data values for this material. Let's see, I don't have everybody's picture up here when I'm sharing my screen. So if you have any questions or you have an issue understanding what I'm saying or want me to slow down or recover something, please go ahead and speak up because I don't necessarily see everybody's hands.
There's a question in the chat, Frisco, or
Is
2
there?
questions. Is the original ICSD database free, and are there only 60,000 compounds in the ICSD?
Good question. So the ICSD database is a separate it's a separate research project to us. We leverage their materials, and we have calculated a lot of what they have. We've done some filtering. We've gone through and curated the results that we find interesting from ICSD. The original ICSD is not free. It is a paid subscription if you want to get access to all their data. So it's one of those really good resources that is available, but it does cost money. And sorry, what was the second question?
Whether there are only 60,000 entries in the ICSD or materials in the ICSD.
Yes. So the number of entries in ICSD, so it depends on what you mean by an entry. I mean, if you look at everything that's in ICSD, there are a lot more. However, some of those being experimental results, some of those may not be very well represented. Some of them may have partially unknown values in there. Some of them may be outside the scope of what we can automatically process. So we kind of filter down to the set that we are concerned with, which you can see right here, right? 60,000 entries. I believe, I'm trying to remember off the top of my head, I think it's over 100,000 total entries in ICSD. Anybody remember the exact number off the top of their head?
I do not, but it's more, but a lot of them are also disordered materials, which is a whole nother rabbit hole to climb into. We are working on expanding our CSD set, and we're not fully complete yet, but we're working on it.
Yeah. This is a work in progress, and it will be a work in progress. If you recall back to Marco's introductory notes, 10 to the power of 177 is not a number we're going to get to anytime soon. So we do the best we can to provide the most relevant and interesting materials available. We curate them, we filter them, we look for things that are flawed, we look for things that are redundant, and we try to get everything limited to that which is of greatest scientific interest. So in getting back into that concept, our data is large and growing, and we're very concerned with sort of what you want to do with the data. So as a person, you'll want to explore the data and you'll go, well, what is available, right? We have these property filters. These are the properties. For every entry, we have, I want to say, somewhere between 130 to 160 properties. I don't recall the exact number. It varies based on certain types get calculated for certain things. But on average, I'd say we're about 150 or 160 properties per entry here, right? And each of those properties has been categorized for you into these higher level categories. We have electronic properties, of which we are showing both the band gap type and the band gap value, okay? We have magnetic properties, mechanical properties. Oop, that kind of exploded. Yep, see, lots and lots of mechanical properties. We have thermodynamic properties. We have relaxed structure. Our calculations take an input and optimize it to its ideal result. We want its minimum energy state. So we take the relaxed unit cell or supercell, and that is what most of our data is built from. We also have the original input data as well, but for the most part, we're looking at the relaxed structure properties. We have, oops, scroll back up. Okay, we have chemistry. These are additional values, and we have calculation details. This goes into what it took us to calculate and how we processed the inputs to make things better for you, the data exploration scientist, right? You want to build models, you want to explore properties, you want to predict novel considerations. You want to know how the calculations were done so you can repeat our work, right? And that's another thing. We want to have our work be repeatable. We don't want to just publish a paper and call it good. So we have lots and lots of properties, and we try to expose everything that is meaningful in our calculation. All right, so I'm kind of getting a little over my time here on this part. I'd like to speed up a little bit. So I'm going to scroll down a little bit. We have the ability to reset the search, right? You want to clear everything.
Frisco, there are a few more questions that came up.
Thank you.
The next question I can take as it relates to what we're talking about tomorrow. What if I want to use 3D materials like graphene? Can I generate them from the AFLOW database? We have a prototype encyclopedia that is focused on 3-dimensional structures. And I think AFLOW itself has the ability to generate slabs. So you can, yes, you can do it indirectly. The next question is the difference between the ICSD query and the all of AFLOW query. Can you just mention that in a sentence or two?
Yep. So as you noted, as somebody observed earlier, the number of entries that we expose from ICSD is just over 60,000. If we were to switch to all of AFLOW, you'll see that number goes up drastically. That means the searches will be slower, you'll get more data back, et cetera, et cetera. We go through and try to predict lots and lots of structures. So just the experimental input is insufficient to sample the entire space available in materials in terms of as he noted, the combinatorics of the species, the structures that are available, and you know, there's a lot of other considerations that could explode this search space very, very large. So we try to make sure that we stick to the most relevant bits. So ICSD is the stuff that has been experimentally defined, whereas all of AFLOW becomes stuff that is more theoretical and under consideration for other possible scenarios. Our work, our database has led to the creation of experimental novel results. And so this is a very valuable thing, but you have to realize that when you're exploring a theoretical possibility, the number of available calculations that you would have to do gets very large very fast. So we try to make it relevant to the end user, whether or not they're looking at stuff that's real versus what's theoretical, right? So I hope that answers the question about the difference between ICSD and all of AFLOW.
Next question is if it's possible to predict electronic properties of chlorophyll-like large organometallic molecules.
Is it possible to predict? So we have a number of projects. There are predictive properties that are based out of machine learning models. There are predictive properties based out of predicted structural prototypes that Marco alluded to earlier. I'm not familiar with the exact chemical structure that you're talking about, but does anybody else have any input on that particular structure?
The short answer is yes, but we don't have organometallics in our database because that's not our research focus. Generally with AFLOW, anything that you can do DFT on using a plain wave code like BASP, you can. Whether or not you should use plain wave DFT on chlorophyll is a different question. Molecular quantum codes might be more suitable for the job, depending on what you're trying to do.
Yeah, metal binding to organometallics is actually kind of a tricky problem. And it sometimes takes special consideration that needs to be examined individually and does not lend itself well to a high throughput framework. So
you may be better off using Gaussian than BASP or quantum espresso, unless you're looking at a chlorophyll crystal. The next question is, or the last question here is, if the properties are from DFT or if they are experimental properties when referring to the ICSD compound.
These are all DFT calculations. All of our properties are, we take an input structure, species, atomic positions, we use specific pseudopotentials, we calculate the DFT results, we converge those results, and we extract the values from them. So we are not actually repeating ICSD's values. We are calculating from the ICSD, if I may, the sort of primitive input of what ICSD is, and then we compute a theoretical DFT calculation from that input. So these are not the direct experimental results, no. Does that answer all of the questions so far?
Those are all the questions, yes.
All righty, all righty. Okay, so once you've performed a search, you might want to clear it out and start over. This is what the reset search button does. That's kind of obvious. This is the way that the search is organized internally. This is our backend engine. We'll be getting into that in much more detail in just a few minutes. And so, yeah, I think at that point, I've got a few examples in the exercises if people want to try. Let's see, what time is it? How am I running slow? Am I running fast? Let's see, it's already 10:38. Let's try searching for something out of the initial exercises. If you will, I think you have the slides from this session. You should have 3 exercises at the beginning. We already sort of looked at the manganese bromide exercise. If you would like to try that on your own, please do. That should be relatively quick. And then try exercise number 2 to see if you can find the bulk moduli for materials containing titanium in the ICSD catalog of the AFLOW database, right? So I'll give you, I would like you all to give that a try on your own, just as sort of hands-on, get familiar with what's here. And I'll give you a minute or 2 to try that, and then I'll go through it as well. wish my display of everybody actually showed everybody. That would make things a lot better. Here we go. I had my Zoom settings wrong. Okay. Now I can see you all again. All right, I'm assuming you've all had a chance to play with the interface just for a few seconds. If anybody wants a little more time to do that, go ahead and raise your hand and let me know. Otherwise, I will jump right in. All right, so
Sorry, Frisco, please, I have a question.
yes.
So once you do this search, how do you download the data?
It depends on which data you're interested in seeing. For instance, let's go ahead and dig into this search a little bit, right? So we're looking for all of titanium, all the, let's see, did I reset the search? I did, okay. So we want the titanium, that's weird, reset didn't take out the, we want to see titanium, and we want to search for bulk moduli. And let's see, this example, I have to confess, I have cribbed these notes from Marco. He's done this lecture in the past. And this example for titanium looks like it's a range of species. Let's consider 1 to, I don't know, let's say 4 containing titanium, right? And then down here, we want to find the bulk moduli, the BRH bulk moduli. So one of the quick and easy ways to see what property is available for bulk. Why did that not work? Sorry. Here we go. Okay, so our filters show this, and we want to see the bulk modulus, right? So we can perform the search, and you will see that the response data found here is 171 entries containing titanium. We want to sort by the, sorry, pardon me. We want to sort by the highest bulk modulus. So if we click on this column, we see that the highest is the iridium-3 titanium material, and it has a bulk modulus of 289.5. Now, if you want the full data, for instance, you can click on the entry, and this is actually something I should have touched on earlier, but I just opened that in a new tab, and you get the full result of this material. We can explore it visually. We have the graphical representation of its structure. We have all of the properties here in different cards that correspond to the filters that we saw in the search page. So you can scroll down through this and see all of these values. Now, this is great for a person to see what's what and get an idea of where they're exploring. But when you want to try to feed something like a machine learning model, this may not be so great because, say, copy and pasting or what have you from this page could be rather time consuming. And as we get to the next section of my talk where I'm exploring the AFLUX API, I'll show you how you can retrieve these properties in a more automated way. So so that you can feed your, say, machine learning models or what have you with all this data in a nice programmatic manner. Does that answer your question about retrieving the data?
Yes, it does. Yeah, thanks.
All right, so The last example was to find the shear moduli, the VRH shear moduli for materials containing at least one halogen, but no chalcogens, right? So in the ICSD catalog, right? So, oops, where's my mouse? I lost my mouse. Okay, so let's reset the search. We're in ICSD. Let's clear this out. Lost. Okay, so we want the shear modulus. So we want to, we can stop looking at the bulk modulus here, right? If you do a search for shear, why does that do that? We do a search for shear, and we see that the VRH shear modulus shows up. So when we search for it, we can add that to our filters. And we want at least one halogen, right? So we look at our groups, right? And we want to include the halogens, but no chalcogens, right? So the chalcogens are, I shouldn't have clicked that button, sorry. We can search them by group name, but we actually want to exclude them, right? So we click the not, which gives us the exclamation point, and then we hit chalcogens. And now if we search, and I'm only searching through the quaternaries here, we want the highest and the lowest. So if we click on this column, we see that the lowest is 0.6525. And if we click again on the column, we see that the highest is 80.89. So in terms of human exploration, this page makes it fairly easy for you to sort of point and click your way into our database. Now, this is good for you, but not necessarily good for your programs. So before I jump in, does anybody have any further questions?
Hello, I have a question.
Yes, please.
Yeah, I'm kind of confused. I understand that the data we're seeing here on this ICSD are theoretical data. My question is the initial inputs that is using in producing these data, are they from experiments or are they empirical?
Yes, so the ICSD database, those structures that are fed into our database are the experimental structures observed by those research projects, right? They feed they take their experiments, they examine them, they determine the structures, and they feed it into the ICSD database. That input is what we build our calculations from. So this is the theoretical result of the experimental input structure.
Okay.
Does that make sense?
It does. It does.
Yes. Okay. Hope it answers your question. So, anybody else? Okay. So let's jump into the next section. The next section will be best served by exploring the AFLUX summons. This is where we're going to be getting large data sets out of our database in a programmatic way, right? So we're going to be using the AFLUX summons, which you see here at the bottom, as I mentioned earlier. You can kind of get an idea. Everything that you're searching for is available through our AFLUX API. Okay, and the easiest way that we can explore this is through the Jupyter Notebook session that Marco has so kindly put together for us. So if you can take a moment to load up your Jupyter Notebook, it should have been, your Jupyter Notebook file should have been made available to you earlier, and load that in with the Jupyter Notebook kernel. It should pop up in your browser. I'll give you a minute or two to load this in. And if you have any problems doing that, please let me know. All right, I'm going to assume that everybody's managed to bring up their Jupyter notebook at this time. If anybody still needs any additional time, please raise your hand or speak up. Okay, very good. All right, so we've already sort of been exploring the web interface, and I think I'm running a little bit fast on my, or rather a little bit slow on my presentation. So I'm going to kind of skip through the exercises that we've already started exploring in terms of what the search page can do for you. And I think some of this is actually overlapping with what I was talking about earlier. So the examples here are asking for perhaps additional properties like whether or not a property that you've searched for, or rather a material that you search for is a metal or an insulator. That's another one of the filters that you would be able to apply to your search, right? So I suggest taking time to read through the filters to get used to what properties are available. But I am going to skip ahead and start talking about the AFLUX search. Okay, so instead of trying to see things graphically, which is pleasing and easy for you as a person, you are going to want to work with our data through some data infrastructure, through some programming interface, some programming language, whatever application you have in mind, right? So we built this API in a way that decouples it from any particular framework. We don't want to be bound to one specific programming language or one tool. We want to keep this in a nice abstract presentation so that you can use it in any tool that you find interesting. So we developed the AFLUX search language, okay? The AFLUX search language is built of two pieces. Can you see is this readable for everybody? Assuming I haven't changed the font size.
Yes.
Okay, so the AFLUX search is built on two basic pieces. We start with the matchbook, which is a set of matching properties that we are interested in. And then we follow that with a set of directives that tell us how we want to present the data. And there are a few different ways that we can manipulate the data that comes back that are of interest and may be essential to whatever it is you're doing. It's highly dependent upon what your application is. However, the part that is the most important is the matchbook, right? This is essentially the same thing as the filters that you saw on the web search page, but it's made in such a way to be programmatically generatable, right? You can take this and build up your request very easily. So for instance, the first cell in the Jupyter notebook is set up for you, where we have the request that's made to our web API. It's completely abstracted from any particular system. All you have to do is be able to make a connection to a web port and submit the request. So this is our server, the aflow.org server. And here is the actual structure of the AFLUX summons. This particular cell, we'll go ahead and run it, which is for a Windows system that should be Control-Enter, and for a Mac it should be Command-Enter. We run it, we see that it generates the URL. You could actually load this in your browser directly. You don't actually need a framework. You can do this with any application that you want, command line tools like curl or wget, programming languages, etc. Anything that can talk to a web page can load our data. And the data comes back as a JSON structure by default, okay? So when we make this request to get the properties, this is our help directive that requests the list of properties that are available. You can scroll through this and see the names of all of the properties plus a description, the units, and those are the big pieces that are important when you are searching for something, right? So you can scroll through and you'll see that we have lots and lots and lots and lots and lots and lots of properties. Perhaps a little bit overwhelming. So I would ask you to come back to this later on and explore it at your own leisure. But this is a way that you can get a list of everything that we expose in our database with a short description of what it is, okay? Following on to that, let's break down the AFLUX summons a little bit more. We've already applied the help directive to explore the properties. There's also a number of other things you can do. You can just say help. You can say help on help. You can say help on. You can explore that with different summons if you want at your own leisure later on, but let's continue on. The next directive is the format. This tells us what the structure of the data in the response should be. If you want to see the data in an HTML structured layout, you can submit a directive of format HTML. By default, everything we have is JSON. One thing to note with that is that the format JSON, as you see here, is a way, if you're exploring this data with, say, the Chrome web browser, the data will come back, and if you don't submit the format request as JSON explicitly, it does come back as JSON, but what happens is you get the data. Let me look at the raw data and take out the format JSON directive. Quit that. Okay, if you're in Chrome, this is what you'll see. You'll see a page full of stuff that is very hard to read. So in order to pretty print this, now Firefox will do this for you automatically, but if you want to pretty print the result in Chrome, you will see it will look like this. This makes it much more approachable by you. It uses a little more bandwidth, but otherwise it's the same information, okay? Let's see, and the next directive that we want to talk about is paging. Paging controls the number of entries and the page of entries displayed. Our database can return a lot of data, so we need controls on how much of that data is returned at any given time. All right, so that's enough to get you familiar with the directive. Let's look at the operators for how you combine our matchbook requests, right? When you're submitting a request, just like the main web page, you have the ability to say something and something else, or something and not something, or something, or I should have said or something, in any structure that you see useful, right? So you can query our database using these logical operators to find properties that are selected down to your specific use case. We try to give you the ability to drill down into our databases as cleanly as possible. All right, so we have grouping operators, the block, open and close parentheses that allow you to combine multiple logical operations in a group and then operate on that group logically with other groups or other individual matches. We have I'll just go through these. We have block and or not. Loose, we haven't touched on loose yet. We'll be getting into that. We have string and we have mute. Now, let's just keep those in mind. We'll be touching on them briefly once we get further into the notebook. Important properties. Like I said, our search is primarily organized around the species. This is the sort of the first introduction to what you want to do. It's either species or groups of species typically that you're concerned about. So, you know, that is a property name, species, that you will be using a lot. The next is how many species are you considering in your response? Do you want binaries? Do you want ternaries? Do you want quaternaries? So the number of species property is n species, and you can then set the value or values there. The next property is the catalog. We've already been exploring the ICSD catalog. And so if you need to restrict your searches to just ICSD, you'll be using the catalog property. By default, AFLUX searches our whole database, which is again why we need the paging directive, because sometimes you could get a lot of data. The property of band gap, the band gap value is of interest if you want to make sure that the material you're looking for is a metal or an insulator or a semiconductor or the like, depending on your application. We'll also be looking at the total spin per atom. This is part of what we compute and make available to you in our database. Anybody have any questions regarding that so far? I'm just trying to go over a few of the things you can do with AFLUX.
The question is, are these 5 properties the only available in AFLOW?
The answer to that is no. We have approximately 150 or 160 properties. That number changes as we add new research into our project. And you can search on any of those properties. That is if we scroll back up and look at this, these are the list of properties that are available. So here we have we start with the AEL, applied pressure. This is a property that is available to you. This is the units. You could scroll down. This list is quite long, but we expose all of the properties in this list. So you can scroll through, look at things, read the descriptions, find the one that you need, one that is of interest to you, and use that in the AFLUX search. This is just a select few of the properties that we will be playing with. Does that answer your question? Hope so.
Yes.
All right, thank you for the question. And let's go ahead and jump into the first notebook cell here. Rather, not the first, the second notebook cell, but the first one where we will actually be searching for materials properties rather than just exploring the structure of our information. In this, we want to see compounds containing chromium and have 3 species in them, right? So the way we would do this was we will type in species. We will put in the atomic abbreviation chromium in parentheses. We will create an and condition, and we will look at n species, and we are concerned with materials that are composed of 3 species. Okay, so we've just entered the matchbook species chromium, comma, n species 3. And I will put that into the chat for you if I can find my chat box.
Catalog ICSD, Frisco.
Sorry?
Catalog ICSD.
Yeah. So catalog is one of those things that I overlooked as a matchbook because originally it was a directive. It was actually designed to be either or. And if you're interested in the structure of the AFLUX language, I would request that you go read the paper. It details the layout of the AFLUX language in detail. So catalog, ICSD. Okay, so thank you, Marco. I overlooked that one. All right, so here we have the directive the directives, paging 1 and format JSON, right? So if we go ahead and execute this cell, you will see that we get 862 compounds. All of them will contain chromium, and there will be only compounds that are composed of 3 species. In the first one, we have silver, chromium, and oxygen. And I'm not going to scroll through all 862, but this is the structure of the data you get back. It's a JSON response. It is labeled for you so that you can see how many properties you're getting back. And let me just scroll to the end very quickly. You'll note that we stop at 64. And this is because we've only requested the first page up here, paging 1. By default, pages are of size 64. You can request other pages. We'll get into that in just a moment. All right, any questions on that? Hope that's clear. I'm going to proceed onward. Now we want to exclude oxygen from the results, right? We have our matchbook up here. And we want to exclude oxygen from the previous search, right? And the way to do that is to come into the species property and say, and the comma operator is the and operator, and not, the exclamation point is the not operator, capital O. O is the symbol for oxygen. Right? And if we execute this cell, again, it generates the AFLUX request, and we now have 550 results. Pardon me. And if you were to scroll through and go through all the pages of these responses, you will find that none of these compounds contain oxygen. So this is a way for you to select materials that are particularly relevant to whatever it is you are attempting to accomplish. And it's hard for us to know sort of a priori what you want to do with our data. So we are exposing these tools to you so that you can make reasoned selections on our data, as opposed to just getting back way too much information and then trying to figure out how to filter it down yourself. So not only does it help you, but it also limits the burden on our network and our server to only give you the information that you are particularly interested in. All right, moving forward. We want to list compounds from the ICSD catalog containing chromium or manganese and 3 species. Okay, so this is very similar to the first search that we did. I'm just going to paste that search in again. We're still looking at 3 species, so N species is 3. We're still looking at catalog ICSD. We're still looking for chromium, but now we want to include manganese, but we want to do it as an OR. We don't want both chromium and manganese. We want chromium or manganese, right? And so the OR operator is the colon, and we add in the atomic symbol for manganese. And if we execute that search, the search will go into our database and return 2,378 responses. Okay, so if you scroll down through this, this is not an exclusive OR. You actually might find that species, or rather materials that come back with the species chromium or the species manganese or both. So this is not an exclusive OR, this is an inclusive OR. And you will get these responses in your data. Does that make sense? Is everybody happy with that so far? Okay.
Yes.
Yes. Very good. Scrolling down a little further in the Jupyter Notebook, we want to retrieve compounds from the ICSD catalog with 3 species containing chromium and selenium or chromium and tellurium. Okay, so this is, again, this is not too different from our previous search. We're just going to paste that same search into our notebook, and we're going to modify this search request. Now, the structure here is we want chromium and selenium as a group, or chromium and tellurium as a group, right? So let's put a group around the chromium, and we're going to add to that group selenium, okay? My parentheses are not behaving well. I think Jupyter is not liking me, but we want the OR operator. We're going to start a new group. And we want chromium and tellurium, right? So chromium and tellurium, right? So all we've done is modify the species property match criteria to be a more complex logical operation, right? We can issue this request as is. If you're familiar with Boolean algebra, you could actually factor out the chromium and restructure this request. Let me go ahead and run it this way. And you'll see that there are 115 compounds. And because of the nature of OR, you'll find that you get chromium and selenium or chromium and tellurium. Now, let me retype this for you as a factored request. I could type it this way: chromium and selenium or tellurium. So I've simplified this request a little bit. All of the Boolean algebra is available to you to play with in your search. Let's go ahead and rerun this. And you'll find that you should get, yep, 115 compounds. It's the same search, just slightly refactored. Okay, so however you're comfortable thinking about this in terms of constructing your Boolean directives, your Boolean match criteria, AFLUX will try to work with you to give you what you want. Any questions on the logical operation so far?
There's one. I also have a comment for people who have errors with broken URLs. Make sure to not include any like space characters in your matchbook. That will break the URL. There's the question here is, how deep can these logical operators go in a request?
How deep do you want it to go? In theory, this is as deep as you want to go. I don't know that we've tested things that are, say, nested logical operations that are 10 or 15 or 20 levels deep. But in theory, the engine behind this should handle any Boolean logic that you throw at it. Does that answer your question?
Yes.
Okay, very good. If there's nothing left on the Boolean relationships, let's move on. Excuse me. We're going to jump into the next operator that is important to us, and that is what we call the loose operator. This is it is represented with a star. If you were to scroll back up, you would see that the asterisk is the operator that we use for loose. Now, we're going to, in this example, retrieve the band gap for all quaternary compounds, okay? So we are going to take advantage of AFLUX's automated processing to query the whole database. So we will not set a catalog. It will just automatically question everything that we have. And the property that we want to get is the band gap. The band gap property is EGAP. Now, if we were to just request EGAP, we will see all of the values that are in our database, and we're going to do n species 4. Right? So this is the search that we want to see, right? We want to see the band gap, and if we execute this cell, submit this into our database crunches on it for a few seconds, and we get an answer, a very large answer potentially. Now we're only requesting page 1, so you don't get all of this by default. But you can imagine that if we did hand back everything, you know, this would quite possibly kill your browser. There's far too much data for a browser typically to handle, unless you have a very powerful system with lots and lots of RAM. We don't want to be mean to most of our users, so we page everything down to make it consumable in handleable quantities, right? So now, there's another problem here. If we look at the EGAP property that we requested, we see that the answer is null. And that is because we have not computed EGAP for all of our materials. Some of the materials do not have EGAP calculated. So since you are concerned about EGAP, let's copy and go down to the next cell and paste, because we're going to be modifying this matchbook. We want to see non-null results. And this is where the loose operator comes in. By specifying asterisk as the match property, we're saying we want something, we just don't know what it is. And so we put the asterisk in there and we execute this cell and let the database grind for a moment, and we have a much more manageable response, only 8,222 responses. So the loose property is helpful in terms of getting non-null results, but it's also much more powerful. If we were concerned with finding a specific EGAP, or rather excluding a range of EGAP values, EGAP is a numerical criterion, a match criterion. And so what we want to do is search only for EGAPs, for instance, that are greater than or equal to 1 electron volt. And the way we do that is we specify 1, and we apply the loose operator again. You can think about this as sort of like a number line and matching everything above 1. Right, so we've selected that and we execute this cell. Submit the request. We should find that our response is smaller still because we've excluded anything that is less than 1 electron volt. And you will see here that we start at the first answer. The first material answer is a EGAP of 1 electron volt. And if we scroll down, it grows 1.003, 1.0036, et cetera, et cetera. So we have selected our set of materials to be equal to or greater than an EGAP of 1 electron volt. Good so far? Any questions? Not seeing any, not hearing any. I will continue on. All right, so
There was a small question about the catalog star.
catalog star is not necessary because AFLUX searches everything by default.
Exactly. Thank you. That's good.
So the default behavior is to give you everything, whether you want it or not. And that can be good or bad, depending on how good your search is. Now, being able to set a lower limit on your range is all well and good, but sometimes you also want a limited upper bound and lower bound range, right? So again, we're going back to the concept of logical operations. Here we have a request where we want to see everything that is greater than 1 electron volt and everything that is less than 3 electron volts. So if let me copy and paste the previous search, because I am prone to errors in typing. So use this as my basis. We already know that we want to be greater than 1 electron volt in our responses. And the comma operator, we want to be less than 3 electron volts. By placing the loose operator before the 3, we're saying everything to left of 3 on the number line. So sort of visual correlation here. You can imagine a visual correlation to the way the loose operator applies to the number. And we're combining that with an AND operator. And now we're requesting eGaps that are inclusively bounded from 1 to 3 electron volts. Let's go ahead and execute this. And if you're paying close attention, you might see that this takes a little bit longer. And if you look at the directive, you'll see that the paging 0 operation has requested all of the data. By requesting the 0th page, that wouldn't normally make sense. We've overloaded that to be the result that contains everything. Now, this result is 3,000 entries, and you can scroll through this. We are well above 64, as you can see. Keep scrolling. This is small enough that it won't kill your browser, but it's large enough to be a little bit of a pain to manage. So be careful with paging 0. But you'll see that if we scroll all the way to the end, that our eGap hits an upper bound of 2.9998. So we do not have any property, rather any materials in our database that are exactly 3 electron volts. This is as close as we get. So there is no 3 electron volt gap. However, we do still start at 1 electron volt, just like we had previously. So these are all of the materials that have 4 atomic species, and their structure has between a 1 and 3 electron volt gap. All right. Any questions on the loose operator so far? I will mention as an aside, we can also search on strings, and the loose operator applies to strings, but I'm not going to cover that explicitly. You're welcome to play with that and ask questions later on at your leisure. I highly recommend reading the AFLUX paper if you want to dive into all of the variations of what AFLUX can do. So moving on, we have the string operator and the mute operator. I just sort of alluded to the string in the loose context, but let's look at it in the just the simple string context. So imagine you're searching through our database. And for instance, you wanted to look, you knew already, because say you read a paper, that the AFLOW unique ID, the AUID for the material of interest is this one, for instance. Right? We have AFLOW : and the unique signature of that material, right? So we want to find that material in the database. We want AUID equal to, oops, I did not copy, hold on. Let me try that again. AUID equal to this, all right? So you go in, you think, great, this is all well and good. I want to find this answer. We execute the search and nothing, which makes no sense. Clearly it exists. What have we done? We've made a search that says we want to see AFLOW or this index signature. Because we don't want to apply the OR operator here, this is actually part of the labeled value, we need to apply the string operator, which is just the single quote. By putting the string operator onto this search and reissuing it, we find that we get the answer that we want. This is the property. We can see up here that we've matched the values. It's the same thing, all well and good. So you can find your way into the string context, even if that string does include AFLUX operators. Any questions on that? Fantastic. All right, where's my time? I think we're okay. Hopefully we're okay. I'm going to try to work through the rest of this. The mute operator. The mute operator is particularly useful when you're digging through large data sets and you, for instance, don't want to see something that you already know, or something that is of no material interest to what you're trying to accomplish. For instance, all of our responses so far have been labeled. When we put in a paging request, we get a named index of where that material is. And we can mute the, sorry, let me paste this in. For instance, we know that this is what we want to get, but we don't actually want that in the result data, right? We could suppress the result, the string.
So you need double quotes around it.
Oh,
because
right.
Single quotes on the string.
This is, yeah, yep. Stop it. Quote mismatching. Why is Notebook trying to be smarter than me? Okay, so if we were to submit this request with the suppression operator in front of AUID, we'll see that we no longer have the AUID in our response. This can clean up your response so that you're not getting back the default values, which you already know should be in place. I think maybe I jumped ahead a little bit on that one. You can also suppress the paging. Let's submit this request once again. Oh, try once more. That is not what I wanted. All right, why? Moment. There we go. Okay, so that's the same matchbook we submitted previously, but let's also suppress the paging directive. By suppressing the paging directive, execute this cell, we will see that we no longer get labeled responses, right? So we've cleaned up the data even more. You can continue to eliminate things that are redundant in your data set so that your processing can be made easier. Any questions on the suppression operator?
Frisco, if you allow a quick comment, this is especially useful if you have, for example, a query that says end species is 4. You already know everything is going to have 4 species. So if you want to reduce your response size, suppressing end species, but still filtering it with the mute operator is going to significantly decrease the amount of data you get back, especially redundant data. That's that's a way to use the mute operator very effectively.
Yes. Yeah, end species, any property can be suppressed in the response. It basically just eliminates it, right? So that cleans up your response data nicely. All right. So now let's move out of the matchbook description into the directives. All right. So we've already played with some of the directives a little bit above. Let's look a little bit more at what, say, the paging directive can do. The paging directive gives us the nth page of, by default, 64 entries. So if we said here in the directive section, paging 1, which is what we've been doing all along, right? We would get the first page, let's run that, of the answer that we had above, right? This is the E gap of quaternaries, where the E gap is between 1 and 3 electron volts. We still see the same 3,000, but if we were to scroll down in the response of this cell, you'd see that we stop at 64 and scroll to the end. Yes. Now we could say, request that, you want to get the second page, right? You want to get the next set of data. You change to 2, you re-execute the search, and you will get the properties indexed from, and it starts up above at 65 and continues on to 128. So you can work your way through the data response set. This particular set is just over 3,000 materials. You can keep requesting the data set until you get, let's see, I want to make sure I'm not, yep, okay. You can keep requesting your responses page by page until, let's say, for instance, we wanted the, get to the, we've looped through the responses and we've got all of our data, but I don't recall off the top of my head, but pick a page number suitably high and we execute that, you'll see that you end up with a response that is empty. Once your response is empty, you know you've got all of the data. So you can loop through page by page, requesting the next page and the next page until your response is empty and you know you're done and you no longer have to keep requesting. Anything that is outside the available response will just return an empty response set. Okay, so now we want to change the size of the response. Let's say you have a reason that you don't want 64 materials in a particular page, right? So let's go back to 2 up there. I'm going to re-execute that just so I can show you something. Let's say you want your page to be of a different value. There's a second value you can pass into paging. You can say, let's ask for the 4th page of 32 materials per response, right? So you can change the size of the page And if you submit this request, this summons, you will find that this one didn't scroll to the bottom. Okay, right. We are again at response 128, just like above where we asked for the second page of 64. This is the fourth page of 32. So you can resize the number of responses per page. Just be careful if you try to make your pages too big, you can end up causing problems either on your end in terms of processing the data, if you're, say, doing it through your browser, or you may end up hitting limits in terms of what the server can handle before it times out. So if you're requesting very large responses, things can go wrong. I suggest you pay attention to paging and make sure you work with something in suitable chunks for what it is you're trying to accomplish. Okay, any questions about paging? No? All right, let's move on a little bit. I think I've got enough time to do the rest of this, hopefully. We want to return the results as an array, right? So we have this, this result. You'll see these are coming back as an object of objects, and each object is named for its index. Now, when you're processing information, you will typically want to iterate over an array. So you would suppress the paging operator like we've done previously. Right? I now have the same request, but just suppressed. And if I do that, you'll see that the response comes back as an array of objects. So you can iterate over the array, but you've lost the identifying index. If you scroll all the way to the bottom, you can verify that indeed this is the same material as we had above. It's just we've lost the index. So it makes it simpler for you to process the information. Okay. Return all results, right? We already know that this request is small enough for the notebook. So we will request the 0th page. And since the 0th page doesn't really make sense, it's overloaded, as I mentioned previously, and you will get everything. Scrolling down off the page. All right. We get all of them, all 3,064. Okay, so paging zeros is nicely powerful when you know your search is small enough to be processed as a single request. When you're getting larger requests, many things can go wrong, so use it carefully. All right, now we've been submitting requests into the database, and we've been getting our answers back, but we haven't looked at what another trick that paging can do for you, and that is the sorting order. Just like clicking on the column in the web search page arranges the response, the AFLUX API can also sort the response. And the sorting is, let's see, this is sort in ascending order. So let's just go ahead and do the same request we had before. We'll note that it comes back, as we've already seen, with the same 3,000 responses. But those, and if we pay close attention, we'll see that the EGAP climbs in value. And if we, for instance, wanted to see it in descending order, we can do paging negative And -0 still works. -0 might seem weird, but we're overloading the 0 anyway. So now we are saying, let's change the sort order on EGAP from the lowest value first to the highest value. We're changing it to the highest value first to the lowest. And we submit this request. And after a moment or two, we look at this and we see that EGAP is indeed what we've noticed previously, that the highest value is not quite 3 electron volts, but it is the first data value in our response. So if you're looking for a particular set of answers that are close to your bound, you can use the negative sign to get to the other end of your data set quickly. And as I've already noted, we're sorting by default on the EGAP property, and that is because EGAP is the first property in the matchbook, right? So if we look at this, right? If we request the negative first page, or rather the descending order first page, even though we've included another property, we are still sorting on EGAP, right? So EGAP being the first property in the matchbook determines the sorting criteria. If we were, for instance, to swap the order of the matchbook so that spin atom comes first in the matchbook, followed by the EGAP criteria, and I'm going to put it in, even though it is the, let's say the negative first page, right? We'll get an answer where we have the maximum spin per atom, right? So now you can find the largest spin per atom. You've got all 64 responses, but perhaps you don't want all of them. Perhaps you only just were concerned about, you know, the limit, right? So you do something like, give me a page size of 1, and I will find the extrema of this data set, right? I have the largest spin atom by sorting by descending order, returning only the first value, and putting spin atom as the first property. I found the extrema of my data set. All right, any questions on sorting? Awesome. All right, the next thing we want to consider is aliases. This is something we haven't touched on previously. Aliases are particularly useful when you're trying to find materials that have large numbers of species in your search. For instance, this search is for zinc blend materials that are composed of a metal and a chalcogen, right? We have 4 species in the chalcogens, and we have a lot, that's a technical term, of species in the metals. Typing all of this out would be painful, right? There's many, many, many metals. So, you know, doing it by hand, yes, it can be done. We can execute the search. It's not very elegant looking. But there you go. We do that search. We find there are 350 materials that match the criteria that we have specified. Okay. And for some reason, this one is expanding to everything in the notebook. How strange. Okay. scroll down. I don't know why that cell explodes. Must be a feature of Jupyter somewhere, something. But we get to see all of them in their wonderful glory. All right, oh, too far. Ah, no. Okay, try that again. 100, 200, 300, 330, 343. Oh, okay. All right, we got down to 350. All right, so that search was not very appealing to type, but you can search with the aliases for those species. We have chalcogens, we have metals, we have all of the names that were in the search. If I go back to the search page, this box up here is a list of all of the, is a set of aliases into, where am I? Into AFLUX, okay? So we can do species, chalcogens, comma, metals. And if we execute that search, we will find a much nicer AFLUX summons that gives us an answer that is also 350 compounds and nicely abbreviated for some reason. So aliases are nice. Aliases are useful in making clean, readable searches. These are a list of the aliases. You can also get the list directly from AFLUX if you were to type help aliases. That's also listed in the, so the help aliases request is noted in the help page. And if you want to explore the help pages that are available to you, I suggest doing that as at your leisure after we're done. All right. With all of that out of the way, we've got about 12 minutes left in the session, I believe. And there are 3 exercises that I would like you to attempt to accomplish. I will give you
Frisco, why don't you go ahead and talk quickly about the REST API, because we need it for Thursday, and then we can go to the exercises.
the REST API. All right, so AFLUX is great when you're looking for groups of data. When you want large data sets, AFLUX is definitely the way to go. If you want a single data, then AFLUX actually gets to be a little bit difficult. So the REST API, let's go back to the materials entry page. And if you look at each of these cards, you'll notice that there is a link in the top of the card that will take you to the raw value, okay? This doesn't seem very exciting, but up here you have a direct index into that property value, right? So for instance, I clicked on energy cutoff and we find that we have a URL that you can drill down into to get individual values. It's much faster to retrieve individual values from the REST API rather than going through the database, because the database has to process all 700 and something million properties or 3.5 million entries to get to the single value that you want every time you want a single value. So you will be spending seconds or tens of seconds waiting for an answer, depending on the complexity of your search, to get one value. The REST API is much, much faster. If you're looking for a particular value, it's often cleaner to go into the REST API. Let's see if I can scroll up here. Here we go. And dig out the value that you want, right? So like we went and looked for, where is the bulk modulus? There we go. Wait, oh, there we go, right? So here's the bulk modulus BRH, which is something we looked at previously. And if you know the material and you just want to get to the value itself without going back through the AFLUX database to get to that particular value, you can construct the REST AURL-based reference and just append to the AURL-based reference the property of interest. Right, so you'll notice here is the property name. I don't know, can everybody see the URL that's here? All I've got highlighted is the property AEL bulk modulus BRH. It's the same property name that you would see in the search page. It's the same property name that you would see in the entry page. It's the same across all of our data. The rest of the URL is composed of what we call the AURL with a minor correction. Let me get back to the AURL. Up here in our database, we store the AURL reference, and it is a normal AURL with the minor exception that the colon after the server name must be replaced with a /. If we were to look here, you'd see that aflowlib.duke.edu / aflow data is the URL, and in the AURL, it is aflowlib.duke.edu / aflow data, blah, blah, blah. So once you have a set of AURLs of materials that you are interested with, and you want to just drill down into a specific value, you can make those requests to the REST API directly. Any questions on that?
We also have an example in the Jupyter notebook below
Do
the
we?
extra
Oh,
focus.
where'd it go? I lost it. There it is. I do remember seeing that. But where? Oh, down here at the bottom. Here we go. Yep. So there are some examples here in the AFLOW REST API section of the Jupyter notebook where you replace :aflow data with /aflow data in the AURL, and everything just works. You can request that value. So you can refer to that in your efforts. Any questions? All
Should
right.
go ahead and run the cells for everyone.
The REST API cells?
Yes.
Sure, why not? Let's do that. We just run this. See that it started with a colon. It was translated to a /, and we'll go down here. Run this one. You can see how quickly that came back. It was virtually instantaneously by requesting that AURL translated EGAP property, we get 1.4484 electron volts. That is much, much quicker than trying to dig it out of the database when you're looking for an individual value. And doing it once more here, you are requesting a input file to VASP the cont_car. We can retrieve the cont_car value. If you scroll down to the bottom of the entry page, there was a section down here that I have omitted to mention. Out of that calculation, downloadable files. And these are the files that represent the material, how we process it, the data that we extract from it, et cetera, et cetera. So here you have the VASP cont_car. right? We have quantum espresso geometry. Somebody mentioned using something besides VASP earlier. Ab init geometry, AIMS, the relaxed crystallographic data, the band structures, etc. So these are files that are made available to you to work with. And you can retrieve them from the REST API once you know the URL of the material in interest, right? So you can just go directly request them by name. Okay. All right, I think I have just a few minutes left for you to play with the exercises. So if there are no more questions about the REST API, let's try the exercises real quick. And if you run into any issues, by all means, please ask. We'll be happy to help you work through it.
And since this question came up, we will provide a completed Jupyter notebook. We'll send it to Dr. Akinojo, and he can forward it to you all.
As a reference, correct? Yes, you can see the answers. They may be slightly different from what I've done, but they're more or less the same, and we'll give you a reference for what we've worked through here. So I will be quiet for a couple of more minutes while you process your way through these exercises. I strongly suggest trying them because sometimes you don't know what goes wrong, and I'm here to help. All right, I'm assuming everybody has had a chance to play with those exercises and explore the possibilities. Just a minor note on something that was brought up earlier. I think perhaps the issue about inserting spaces may be related to the notebook and not AFLUX itself. When I make the request on the URL, spaces don't seem to matter as long as the datum in question is not actually broken. For instance, if I was to split ICSD in half, that would probably not make sense. Yeah, that will break, but Otherwise, spaces are accepted directly. Seems to be an issue with the Jupyter notebook interpretation. I'm not sure what.
It's probably URL lib. URL lib might not like anything, any kind of control characters that are not percent encoded.
Correct, correct. Because the browser will substitute it as %20 before submitting it. Oh, okay. And if everybody has had a chance to play with the exercises and you're happy with the results, I would like to go ahead and wrap up this portion of the talk. I want to thank you for your participation. I want to thank Marco for his material that he provided in developing this talk. Made my life much, much easier. If you have any questions about AFLOW, AFLUX, the REST API, or the search page, I am happy to answer them at this time, whether or not they're related to the talk that we've covered so far. And if there are no questions, I will hand back the scepter of power back to Marco, and he can wrap up our session.
Thank you, Frisco. Yeah, today you learned about how you can retrieve the data that we calculated already using a graphical user interface and an API and search through them. Tomorrow, it will be me talking about symmetry, structure analysis, and how to generate structures for your own DFT code, and how to compare these structures and how to get symmetry information that you might be using for your own machine learning models. After that is going to be Dr. Coriosis talking about synthesizability and thermodynamic stability. And on Thursday, we'll have Professor Cormac talking about machine learning. Are there any questions about what you heard today? That does not appear to be the case. With that, you can always ask questions tomorrow in the session. We will all be here again, and that I will conclude the session, and y'all have a good night, and I will see y'all tomorrow.